Hello guys, welcome to this video, and in this one we are going to study about the variance and other properties of the binomial distribution. So as in the last video we have studied about binomial distribution, its PMF, that is the probability mass function, its expectation. I have also derived the expectation, so if you remember I'll just give a quick recall of what we have done. So last chapter was about binomial distribution. So I'll just give a quick review. Binomial distribution looks like this. So a random variable x following binomial distribution would be called as x following bin of n comma p, where n and p are the parameters of the binomial distribution. And we can also see that n is the number of trials. N is the number of trials, while p being the probability of success. Okay, now n is the number of trials and p is the probability of success, and x follows binomial n comma p. This means that the PMF is given as this. So just a quick review of what have we done in the previous chapters. P to the power k 1 minus p whole to the power n minus k, and this goes for 0 less than equals to k less than equals to n. Okay, so this is the PMF for the distribution. So what we have learned is that this PMF is valid for all values of k from 0 to n, which is the number of values the random variable x takes when it is following a binomial distribution. The expectation, which is given like this, expectation, or sometimes we also call it the mean or average. Okay, and this is basically given by e of x equals to summation k equals to 0 to n. I'm writing it specifically for this distribution. In general, you do know what expectation represents, as we have done in the previous videos. So for this one, it should be nck p to the power k into 1 minus p whole to the power n minus k, and there would be a k in the beginning. That would give us the expectation. As our calculations turned out, it became true that np is the required expectation. But now we move forward to find the variance. But before that, let me discuss some of the properties of expectation and in the related things that comes with them, and also the properties of variance. So see, expectation is a linear operator. Expectation is a linear operator. Now the term might be easy to understand, but it is not as much easy as it looks, because a linear operator has its own properties which we need to define. Okay, so defining that, we can show here what a linear operator is first, and then we can move on. So linear operator, a linear operator is a function which, so we can define a function f from d to u, where if you take an element from the set D, which is the domain for the function, let's say for x belongs to D and a belongs to real numbers R, we have f of ax should be equals to a into f of x. Okay, and of course this u here, this u is a subset of real numbers. Okay, this u is a subset of real numbers. It could be real numbers itself as well, but it's just a subset of real numbers. Now f of ax equals to a into fx. Now for a comma b, which are real numbers, we have f of ax plus b equals to a into f of x plus b. So this is the property of a linear operator. A linear operator operates in this way. And since I said that expectation is also a linear operator, it means that expectation follows the same rules as above. So expectation of 0 is 0, first of all. Expectation of ax plus b, where a and b are real numbers, is equals to a into e of x plus b. And for two RVs x1 and x2, we have e of ax1 plus bx2 equals to a into e of x1 plus b into e of x2. So this is how expectations work in general. So they are linear and they can be distributed. So even if you have like a combination of 2 or 3 RVs, they can be done, and it works irrespective of where the random variables are independent or not. Okay, right. So this is the most basic property of expectations, because it's a linear operator and it works like this. The operator e is a function defined from the set of random variables, which we can write like this, to the set of real numbers. Okay, so this completes our definition for expectation. Now on to variance. We have defined previously what the formula for a variance looks like. Now we are going to define it more formally as follows. Variance. The variance of a random variable x following a PMF Px is given by so as we know, we denote variance by var of x, and the formula states that it is equal to e of x square minus e of x whole squared. So the expectation of e of x square minus expectation of x, the whole square of that, right? So this is the variance of x. Now you might be wondering how to find, because we know how to find expectation of x, but we do not know how to find expectation of x square. So I'm going to state a very important theorem here. So this is a very known and popular theorem in statistics. It's called law of the unconscious statistician, or in short it's also called the Lotus. So if you search Lotus Rule, you will find that this is the rule that I'm talking about. And what does it actually say? The Lotus Rule says that if x is a random variable and g of capital X is a function of the random variable such that g of x is less than infinity, of course, then we have the expectation of this function in regard to x can be found out like this. So expectation of the function gx. So we are not really going to find out the expectation of x here, as we know how to find that, but we are rather interested in finding out that we have a function g of x, where x is the random variable and g of x has some form, and we are trying to find what is the average value of that function, right? What is the average value that function attains and not the random variable. So it's a different kind of a question, quite understandable one, but not really sure how to do that. That is why we are trying to use law of the unconscious statistician here, that is the Lotus. It says that this is simply equal to small x belongs to omega g of small x into probability of x. So what does this mean? This means that here omega is the sample space. Okay, it is the sample space. P of x means probability of the event x equals to x, and g of x, you do know what that means because it's just a function. So for any given function g of x, we can always find out how to find the expectation of that function, right? Okay, so this is done. Now we can move forward to find our required expectation for e of x square. So if the PMF is pxx, then e of x square should be equal to summation small x belongs to the sample space omega x square into pxx, right? So this should be the expectation for x square according to the Lotus. And as we have seen in the binomial theorem before, in the binomial distribution, the PMF is given as follows. So probability of x equals to k, and this was equal to nck p to the power k 1 minus p whole to the power n minus k, right? Remember how we use it to find the actual expectation. So this was the PMF for binomial NP. Now when we are trying to find e of x square, it means that we can use e of x square equals to summation k equals to 0 to n k square nck p to the power k into 1 minus p whole to the power n minus k, right? So that's what this means. Now obviously this whole thing here is a bit truncated version, because evaluating this sum is a bit trickier than the previous one as well, because this would involve you to solve and separate this binomial coefficient into two different parts. Although this can be solved using the very well known methods of calculus, which I will try to attempt here just to show you a glimpse of how powerful calculus can be in order to solve any problem of probability. And eventually we would have to learn calculus and integration and differentiation in order to solve most of the problems in the upcoming sessions. But for now, let's just try to have a focus on how to solve this. Okay, so we know that 1 plus x whole to the power n is equals to how much? K equals to 0 to n nck x to the power k, right? Here x is just a real number, consider it as a variable. Okay, we consider this as a function f of x. Now if this is a function, we can derivative it, right? Because it's a polynomial function and n is a natural number. I can just write the natural number thing here so that no one gets confused about this. So n is a natural number means n is a positive integer, which is like from 1, 2, 3 and so on. We can also differentiate this function. So the standard way of differentiating a function is using limits, but for sake of clarity here, I'll just show you how the limit thing works like this. If you evaluate this limit, you can get the answer. So I'll just do this once for you, because all of this will be covered in the calculus section. And this would be 1 plus x plus h whole to the power n minus 1 plus x whole to the power n divided by h, where h tends to 0. And this would simply mean that the answer is n into 1 plus x whole to the power n minus 1. Because when you expand this term, I'll just write it here. Since 1 plus x plus h whole to the power n minus 1 plus x whole to the power n, this thing can be written as 1 plus, the first term can be thought of as 1 plus x plus h whole to the power n. So it's a plus b whole to the power n, whose expansion is a to the power n plus n into a to the power n minus 1 into b plus higher powers of h square into something plus all the way up to h to the power n, right? Minus 1 plus x whole to the power n. So this gives you something like this: n into 1 plus x whole to the power n minus 1 into h plus higher parts of h square, like h square and above. So when you divide it by h, what you get is something like this: f dash x, you get limit h tends to 0, n into 1 plus x whole to the power n minus 1 into h plus O of h squared divided by h. What you get is n into 1 plus x whole to the power n minus 1 plus limit h tends to 0, order of h square and above divided by h. But this term is 0 because the numerator has terms of h square and above, which will cancel up with h to give you OH, right? Like terms of minimum power 1, but h tends to 0, so 0 into everything is 0. So this will give you n into 1 plus x whole to the power n minus 1. So this is a fairly simple way to calculate a derivative. Now once you calculate a derivative, you see what happens here. Since f dashed x equals to 1 plus x whole to the power n minus 1 into n, but also fx was equal to summation k equals to 0 to n nck x to the power k. You can so differentiating this side of the variable, we get still f dash x equals to k equals to 0 whole to the power n nck, and we get k into x to the power k minus 1, where we are differentiating only the x to the power k part because everything else is constant. Only the x part will be differentiated. Now these two are equal because they are both f dash x. Therefore summation k equals to 0 to n minus 1, only n, nck into k into x to the power k minus 1 is equals to 1 plus x whole to the power n minus 1. There is a n here, right? Similarly, if you add a x here, if you multiply by x both sides, it becomes summation k equals to 0 to n nck k x to the power k equals to nx 1 plus x whole to the power n minus 1, right? And you differentiate it again to find this thing: k equals to 0 to n nck k squared x to the power k minus 1 equals to, and now what we get is this: n is a constant, so differentiating this, you get 1 plus x whole to the power n minus 1 plus x into n minus 1 into 1 plus x whole to the power n minus 2. So the final answer here becomes n 1 plus x whole to the power n minus 1 plus n into n minus 1 into x into 1 plus x whole to the power n minus 2, right, for this summation for any value of x. Now if you remember, in this section what we wanted to find is this, right? So we can write expectation of x in a different form here. So expectation of x square can be written as summation k equals to 0 to n nck p to the power k into 1 minus p whole to the power n minus k, and you combine, you can just take the 1 minus p whole to the power n part outside, and you can write this as k equals to 0 to n nck p by 1 minus p whole to the power k. Okay, so writing in this form, what helps us is we can multiply a x here on both sides to get the x to the power k equation, and we can put x equals to p by 1 minus p, right? So what do we get by doing that? We get this, putting x equals to p by 1 minus p, we get summation k equals to 0 to n nck k square p by 1 minus p whole to the power k. This would be equal to n into 1 plus p by 1 minus p whole to the power n minus 1 plus n into n minus 1 into p by 1 minus p into 1 plus p by 1 minus p into n minus 2, right? Let us simplify this a bit further. It would be a k minus 1, I think, yes. Simplifying it a bit further, we get 1 plus p by 1 minus p is basically 1 by 1 minus p. So this is like this, and this is also into p by 1 minus p whole to the power n minus 1. Okay, now we need to multiply a p into 1 minus p on both sides again, which gives us k equals to 0 to n nck k squared p by 1 minus p whole to the power k, because we multiplied this again, so this k minus 1 power become this, and this would become np by 1 minus p whole to the power n plus n into n minus 1 into p squared by 1 minus p whole to the power n, right? And now if you multiply both sides by 1 minus p whole to the power n, it will become 1 minus p whole to the power n into summation k equals to 0 to n nck k squared p by 1 minus p whole to the power k equals to np plus n into n minus 1 p squared. But if you remember, the left hand side here is basically e of x square, right? So you can name this as 1, and you can see here that from 1 e of x squared is equals to np plus n into n minus 1 into p squared, which is np plus n square p squared minus np square, right? So this gives you the whole idea of how to solve certain problems, and the variance here then would be var of x would be e of x squared minus e of x whole squared. So we know e of x square is basically equals to np plus n square p square minus np square, and e of x whole square is np whole square, right? So this terms cancel off, and what we are left with np into np square. You can take np common to write n into p into 1 minus p, which is the variance of the binomial distribution. Therefore the standard deviation of x, which is the sigma denoted by sigma, is given by root over of variance of x In other words, it's just root over of np1 minus p. And this would complete our discussion for the binomial distribution. So you see that this actually becomes a bit harder at the end because of the calculus involved, but still it's a fairly easy problem to deal with. And I think this kind of problems are more often than not found in each and every section where you find probabilities. So that would end our discussion for variance and expectation and its properties. In the next section, we shall discuss about the properties of variance and covariance and correlation, and do a few example problems to clear out all our doubts. So I think that would be it for this lecture, and do check out the Britter Maths app. It's a statistical tool and it's a mathematical app where you can find all the lecture notes regarding this video and related calculators for probability and statistics as well. Check the link in the description. Thank you.